In this video, we're going to be discussing a fundamental concept for calculus. As a matter of fact, each one of the two major branches of calculus is based off of this concept of a limit. Well, a limit is the value that a function is approaching as x approaches a certain value. In this case, we're going to examine the limit as x approaches 3 for f of x is equal to x squared minus 9 over x minus 3. When we write this in limit notation, we're going to write lim x with a little arrow that means approaches or approaching the value that x is approaching, and then you can either write f of x or you can go ahead and write whatever the function is equal to. So we would read this the limit as x approaches 3 of f of x. Now if you take a look at this original sentence right here, you're going to notice that there's something different than just regular old evaluation. If I wanted to have you go ahead and evaluate this for 3, then I would write simply f with the parentheses and a 3 in the middle. And then all you would need to do was take this 3, plug it in, see what happened. If you do that here, and keep in mind this is different, but if you do that, you've got 3 squared, which is 9, minus 9, which is 0, and then you've got 3 minus 3 in the denominator, which is 0. So you get this really funny thing, you get 0 divided by 0. And that is not something we can deal with very well. However, limits can help us with this. A limit, it does not care here, we don't care really about what happens actually at 3. Don't care. The function could exist, might not, doesn't matter. All we care about when we're looking for a limit is what is happening when x gets close to or approaches 3, but not exactly equal to. For a limit to exist, the limit from the left, or the value the function is approaching from the left, needs to be the same that the value is approaching from the right. So if we want to write that in limit notation, we can write almost the very same thing, except there's one difference. And so this is the regular limit from both the left and the right. Have to be the same for this one when x approaches 3. Here we want to approach 3, and we're going to add this little negative sign up here in the superscript position. So you might mistake that for an exponent, but you can say to yourself, well, there's no exponent there. In other words, there's no value, it's just a negative sign. It's not 0, it's not 1, it's just a little negative sign. So in limit notation, this means the limit as x approaches 3 from the left side, or we could say from the left hand. And we'll just put side right down here. Okay. The other thing, we need to put f of x there. We need to take the limit of something. And then the other one we could do is the limit as x approaches 3 from the right. So we're going to come from the right to the left and see what happens when x gets very close to, but not equal to, 3. Again, this one is going to be the right hand, or just the limit from the right side only. If we take a look at the graph of this function, this is a rational equation. So to be able to graph this, we want to find out a couple things. First, what we need to figure out is what values don't work for this. And we kind of said that before. You know, we tried to evaluate this thing for 3 and it didn't work. You'd get 3 minus 3 in the denominator. So you can do the same things you did when you graphed rational equations. And we need to figure out, though, maybe the second thing we need to figure out is what is that? Is it a point discontinuity? Do we have to draw an asymptote? What is going on? And one of the things you can do is you could try to factor. So let's factor x squared minus 9. It's going to be x plus 3 times x minus 3. And in the denominator we still have our x minus 3. So you'll note that in the numerator and denominator we have the exact same factor, which means that the value of 3, the value that makes the denominator 0, is going to be a whole. If we were to cancel those out, we'd be left with just x plus 3. So this graph is going to behave just like x plus 3, except for an x value of 3, the function is undefined. If we go down to our graph, we can apply that and simply graph or a linear equation. at y is equal to x plus 3, or f of x is equal to x plus 3. So if we do that, we've got a y-intercept right here at 3. It's going to be a slope of 1, so we can go up 1, right 1, up 1, right 1, and then here, when x is 3, I know that I need to draw an open circle. Remember, when we have a value of 3 for x, that function doesn't exist. Now, a word of caution, please be very careful when you are graphing this, because your graphing calculator will actually lie to you. It will go right through that value simply because it's pixelated, and it won't tell you that that value actually doesn't work. So be very, very careful. Know how to work with the algebra part of this rational equation. All right, now to more of the limit talk here. So we know that this is the graph of the function, and remember that we don't care about what is actually happening at 3. We know what's happening. It's undefined. We don't know how to deal with it. So for a limit, what we want to do is we want to see what happens approaching from the left and then also approaching from the right. That value has to be the same, and by value I mean the y value, the up and the down value. We know what the x value is, it's 3. We want to know now what is the up and the down value doing, the f of x, the output, the y value. Those are all the same thing. So let's look at what's happening here from the left. So as we come from the left and approach this value of 3, when x is 1, the output is 4. When x is 2, the output is 5. And the missing y value here would be 6. So it looks like from the left, this thing is approaching a value of 6. Let's see if that's the same from the right. So as we come from the right, again, this is the right-hand limit, so you're going to be using this kind of notation here. From the right, let's take a guess here at 6. So when x is 6, it looks like the function would be 9. When x is 5, the function would be 8. When x is 4, the output, or f of x, is 7. The value of the function is 7. And then at x is equal to 3, we can see that this value is coming from 9, 8, 7, and then we would kind of guess that there's a 6 there. Again, the function does not equal 6 at that value. It's undefined, but for limits, we don't care. We just care what is happening as we get close to that value. So it looks like, graphically, we think the limit as x approaches 3 looks like it's 6. Graphs are a great way to start. If the graph is drawn accurately, it can tell you a lot of things. And we're going to apply a little bit more precision, though, here in the next way to look at a limit. So we think that, and I should write f of x is equal to 6. Not that when you substitute 3 and the function's equal to 6, but the limit as x approaches 3, the value of f of x as x approaches 3 is 6. So let's take a look at a table here, and for the table we're going to go from the left first. We're going to pick some good values of x and see what happens to f of x. In this case, we're going to get a little bit more precise. We're going to get a little closer. So if we start with an x value that's somewhere left of 3, maybe that's 2, and then if we get a little closer, maybe that's 2.9, and a little bit closer, 2.99. Again, we don't want to get right to 3. We just want to go ahead and get close to 3. So we got 2.9999 there. And we're going to use our calculator to help us out. And in your calculator, if you go to your y equals button, go ahead and enter that function in. And please, please, please use parentheses around the numerator and, in this case, the denominator as well. Whenever you have a plus or a minus sign in the top or the bottom in between two terms, when there's 2 or more terms, you need to use those parentheses. So if we put this in to y sub 1, we can go back and we can ask the calculator to evaluate some values for us. And the first one is 2. We can go to variables, right beneath your cursor buttons, bottom left of your cursor buttons. Cursor 1 to the right to go to y variables. You can hit enter, it's on function, and hit enter again. And you can see here that that gives us a little y sub 1. And as long as you've entered the equation in y sub 1, we can now ask the calculator to please evaluate that function for an x value of 2. And all you have to do is just use parentheses, and the x value you want goes inside those parentheses, kind of like function notation. And it's 5. So we'll add that on our table. Now this is super easy. You just go to your entry, which is second enter, and then instead of 2, we want 2.9, so we can go ahead and put that value down in the next position. We're going to do that several more times. So the next one should be 5.99. And 2.999 would be 5.999. And if we do the last one, we're going to add one more 9 there. And you guessed it, like we started off with 4 9s in the decimal position, we're going to have 4 9s in the decimal position for our value. Remember, this is the input, this is the output. So x is getting very close to 3, and f of x is getting very close to, looks like it's 6. And again, we've got a little more precision than we did in the graph. So just taking a look at the y values here, it definitely looks like it's approaching 6. So if you wanted to, you could write here at this point, the limit as x approaches 3 from the left of f of x, I hope this is on the screen for you, is equal to, looks like it's 6. And again, we're just wondering what the value is approaching. Let's take a look from the right, and I'll go ahead and start on the right-hand side, so we can go from the right to the left for this one. And if we do that, we can start off with some value that's a little bit bigger than 3. Let's make it 4. And then we're going to get closer to 3, so let's go 3.1. A little bit closer to 3, 3.01. And maybe 3.001. And finally 3.0001. Once again, we can ask our calculator to do this quite efficiently for us. So we can go back to our entry, and instead of 2 with a bunch of 9s, we would like 4. That'll be our first one. And the output is 7. We can go back and do, oops, that'll be 3.1. We're going to get a little closer. So that's 6.1. And we'll go 3.01. So that's 6.01. And you could do this again and again, but you would see very quickly that these would be the values that you had if you did this in your calculator. And so you can also see that as 4 from the right now, so we can do that. We can introduce that notation here as, let's see, the limit as x approaches 3 from the right-hand limit of f of x, and we've got 7 here. As x gets closer to 3, or approaches 3, it looks like the output values get closer and closer to 6. So now that the left-hand limit is equal to 3, or from the left, and then the right-hand limit, or from the right, is also approaching 3, is also 6, we can conclude, at least numerically, it seems like, that the limit as x approaches 3, the left and the right have to agree, is 6. Let's take a look at this algebraically, and I'm going to go back to this step for you right here. This step right here. If we write this down, so we can write down the limit as x approaches 3 of x squared minus 9 over x minus 3. And if we keep our notation going, the limit as x approaches 3 of that factored form of x plus 3, x minus 3 over x minus 3. One of the things that you can do with these limits, one of the many algebraic tools that you can use, is to simply try to factor everything and try to cancel. And we can cancel these out. We're left with the limit as x approaches 3 of just x plus 3. Previously, when we tried a direct substitution, we said, what's going on with this function if x is 3? And it didn't work. However, with a limit, we can try this algebraic technique, and then, after we've tried the algebraic technique, substitute 3 in. So that would be 3 plus 3, and you guessed it, that would be equal to 6. So if you take a look at this limit of this function, even though the function isn't defined at 3, graphically speaking, the value of y is approaching 6 from both the left and the right. Numerically speaking, we took a look at that from both the left and the right, and the function seemed like it was approaching 6. And then also algebraically we can show that the function does approach a value of 6. So the answer to this question, if you're asked this, is just 6. That is the limit as x approaches 3 of f of x.